Now we are going to talk about the relation between focal length and radius of the curvature. Focal length denoted by small f, radius of the curvature denoted by r. Now we are going to find the relation between this focal length and radius of the curvature. Okay, so now I am going to explain. We are going to derive the relation between those. So this is a concave mirror. What is the midpoint of the spherical mirror is called pole. Center of the sphere is called center of the curvature. A line joining the pole and the center of the curvature is called principal axis, denoted by x. The distance between pole and center of the curvature is called radius of the curvature. Whenever parallel beam incident, after reflection all the light rays converge at one point, that is called principal focus. Okay. Now let us imagine a ray coming to incident on the spherical mirror. And how does this ray is coming? This ray is passing parallel to the principal axis. You see the angle between these two is same, always 0. Okay, this ray is not making any angle with the principal axis, so 0. So since this ray is parallel to this one, a parallel ray incident on this. Okay, after reflection what happened? This passes through focus. After reflection the ray passes through focus. Sir, a ray passes parallel to the principal axis, after reflection passes through focus. Why does it pass through only focus? Why doesn't it pass between this pole and focus like this, or between F and C like this? Why it passes through only focus? What is the reason for that? What is the reason behind this? Simple. I will draw the normal now. So normal always passes through the center of the curvature. This is normal. You know very well. The angle between the incident ray and normal is called angle of incidence. The angle between the normal and reflector ray is called angle of reflection. Light always obey the two laws. Okay, the second law is angle of incidence is equal to angle of reflection. Whenever a ray passing parallel to the principal axis, after reflection it passes through focus, because at that particular point only the angle of reflection which becomes equal to the angle of incidence. If it passes through focus, then only this I and R becomes equal. So light always obey this rule, angle of incidence is equal to angle of reflection. That is why it passes through focus. I hope you understand. Okay. Now see, this incident ray meet this concave mirror at one point. That point is called X. So this incident ray meet the concave mirror at one point. That point, let's say X. Okay. Here I am going to draw one triangle. You see, this is the triangle from the picture. Okay. I am showing this triangle. Okay. Yes. Here let's say this is theta, this is also theta, I is equal to r. When this is theta and this also will become same. These are the two sides. You see this side and this side. This triangle has three sides, right? What is the triangle? I am making this triangle XFC as triangle. So triangle FXC. FXC is my triangle. So this one, I'll draw the outline. So this is my triangle, right? How does this triangle look like? This triangle is look like isosceles triangle. So triangle FXC is an isosceles triangle. What is isosceles triangle in mathematics? Triangle has three sides. Okay. If two sides are equal, then that is called isosceles triangle. If all sides are equal, that is called equilateral triangle. Here, this particular side and this particular side, these both sides are equal. That is why it is an isosceles triangle. Okay. Right. So from this, what do we understand? Since this triangle is isosceles, the length of the FC and the length of the FX both are equal. So the distance between focus and the center of the curvature is equal to focus and X. FC is equal to Fx. Okay. Now, due to paraxial approximation, what is paraxial approximation? I will explain. First, what are called paraxial rays? Also, I will explain. Here, we have two kinds of rays now. If you take one spherical mirror this way, this is principal axis. The rays which are passing very close to the principal axis are called paraxial rays. These are the paraxial rays. And the rays which are passing very far away from the principal axis, these are called marginal rays. Okay. So paraxial rays actually meet at one point, marginal rays meet at one point. Both are meet at different points. Okay. But our lesson is completely related to the paraxial rays only, because our lesson dealing with mirrors of small aperture. You see the aperture of this mirror very small. So here one principal axis. Remaining light rays which are incident parallel on this principal axis also considered as paraxial rays only, because we are not dealing with very big mirrors, such a big mirrors. We are dealing with only small mirrors of the small aperture. That is why any light ray which is incident on the mirror is considered as paraxial ray. I hope you understand. Okay. So paraxial rays and marginal rays. So what are called paraxial rays? The rays which are passing very close to the principal axis are called paraxial rays. I will show you. So this is one of the ray. I am taking one of the rays, one of the paraxial rays. This is going to meet after reflection. This ray is going to meet the principal axis at this point. So since these are the paraxial lines, let's say this is focus, this is pole, this is X. These two are equal. The length of the XF and PF are equal because rays are paraxial. But if you take the marginal rays like this, if you take the ray from here, that will meet here. Can we say this distance and this distance is same? This one and this one, can we say same? No. In this case, we cannot say same. But for paraxial rays, we can say the distance between P and F and X and F are same. That is why, due to paraxial approximation, this PF and this XF both are same. PF is equal to XF. Okay. Here Fx, XF. So from these two, we can understand FC. In the place of Fx, we can write PF. So FC is equal to PF. Okay. So P stands for what, Nana? Pole. F stands for what? Focus, principal focus or focal point. FC, the distance between focus and center of the curvature. So the distance between pole and focus is called focal length. This distance equal to the distance between focus and center of the curvature. So this is also can be known as focal length, because since from the derivation we understand that the distance between pole and the center of the curvature is called what, Nana? Radius of the curvature. Okay. So here radius of the curvature R is equal to P to the C, the distance between P and C. But the distance between P and C divided to two parts, PF and FC. Since R is equal to PF plus FC, both are equal. PF and FC both are equal. That is why the distance between pole and focus is called focal length, and the distance between focus and center of the curvature is also focal length. Okay, then R is equal to F plus F, 2F. Okay, this gives the relation between focal length and radius of the curvature. Okay. R, when R is equal to 2F, radius of the curvature is equal to 2 times the focal length, then F is equal to what, Nana? Half of the radius of the curvature. F is equal to R by 2. A simple idea. The focal length of the convex mirror is 25 centimeters. Then what is the radius of the curvature? When the distance between pole and focus is 25, then what will be the distance between pole and center? Double, 50. If the radius of the curvature of the convex mirror is 12 centimeters, the distance between pole and center is 12, then what is the distance between pole and focus? Half. R value I gave you 12. You have to find F value. F is equal to R by 2. 12 by 2. That is equal to 6. Okay? So, this is the relation between the focal length and radius of the curvature. Please note down the derivation part. And especially I am telling you, this relation is worked out due to only paraxial approximation conditions apply. Now, children, we are going to talk about rules to draw the ray diagrams for concave mirror. First, what is the purpose of the ray diagrams? As we have discussed in the previous video, whenever we see our images in spoon, okay, our image completely looks different. Our image looks inverted, okay, size is decreases. Yes or no? Whenever see our images on the curved surfaces, our image size, our object size and the image size never be equal. Okay? So why it appears like that? What is the reason? To understand that ray diagrams, we have to learn ray diagrams. What do these ray diagrams explain? These ray diagrams explain characteristics of the image formed by the spherical mirrors. So, characteristics we can understand practically by doing the experiment in the lab. Okay? So, this kind of mirrors, spherical mirrors, we keep in the V stand. Object is placed in front of this. Okay? Candle is placed, candle is lit. After lit the candle, we have to decrease the distance. Then we have to understand the characteristics of image formed by that. Okay? But how many of the people can do the experiments in the lab? So those who are unable to do the experiments in the lab, they can understand the ray diagrams with the help of, they can understand the characteristics of image with the help of ray diagrams. So ray diagrams help us to understand the characteristics of the image formed by the spherical mirrors. That is the main purpose of the ray diagrams. Okay? Right. Now, rule number 1. So this is concave mirror. I placed it this way. Okay? So this is the midpoint of the mirror, that is called pole. This is center of the curvature. A line joining the pole and the center of the curvature is principal axis, and this is principal focus. We can place the object anywhere on the principal axis. We can place at infinity, we can place beyond the center of the curvature, we can place at the center of the curvature, we can place between focus and center of the curvature, we can place at focus, we can place between pole and focus also. So we can keep the object at different places. But just to recall, in front of the plane mirror we have discussed in the 8th class and previous video, wherever you place the object, this is the object distance. Then image also forms with the same distance. Here the image forms. If you increase the object distance, then image distance also increases. When object distance increases, image distance also increases, because object distance is equal to image distance. Height of the object is equal to height of the image. But can we find the same characters in this concave and convex mirror? Do the characters same? Okay. Let us understand. Do they same or different? After learning the ray diagrams, when you draw the ray diagrams, you will understand the characteristics of the image. Then you will come to, you can draw one conclusion. Are these characters matching with the plane mirror or not matching with the plane mirror? You will understand. See, now we are going to keep an object at one point that is beyond C. Okay, this is object denoted by O. Here P nothing but pole, F stands for focal point, and this C stands for center of the curvature, and X stands for principal axis. Okay, O stands for object. Object is placed here. So from this tip of the object, many light rays are going to incident on the mirror. Many light rays. For example, if this is a concave mirror, if you place the object this way, from the tip of the object, infinite light rays are going to meet. Infinite. But can we take all those? No. We consider only few rays. Okay. One is passing parallel to the principal axis. So I consider that a ray passes parallel to the principal axis. After reflection, passes through focus. Why does it passes through focus? Because if you draw the normal that is passing through center of the curvature, this is normal. The angle between incident and normal is called angle of incidence. The angle between normal and reflector is called angle of reflection. Light always obey this angle of incidence is equal to angle of reflection. During the reflection, it happens every time. I is equal to R. I is equal to R. It is possible when only the ray passes through focus. If the ray does not pass through focus, if the ray passes through some other point, these two angles never become equal. That is why any ray passes parallel to the principal axis, compulsory after reflection passes through focus. Okay, so this is the rule number 1. Okay, what is that? A ray passes parallel to the principal axis. A ray passes parallel to the principal axis. A ray passes parallel to the principal axis. After reflection, it passes through focus. Passes through focus. So now we are going to talk about rule 2. Here I will draw the diagram. You know the denotation. Here object is placed, this is object. From this object many light rays are coming to incident. So previously we have taken ray passing parallel. Now we are going to take ray passes through focus. Okay. Now here we are going to take ray passes through focus. So what happened when a ray passes through focus? A ray passes through focus and incident on the concave mirror, after reflection passes parallel to the principal axis. Reverse phenomena. If you keep one plane mirror here, what happened? The ray which is incident on the plane mirror perpendicularly, after reflection it goes this way. Imagine if the ray passes through focus, after reflection what happened? Passes parallel to the principal axis. So what is happened in the rule number 1? In rule number 2, a reverse phenomenon will happen. Okay, any ray passes through focus, after reflection passes parallel to the principal axis. So this is rule number 2. A ray passes through focus or focal point of a concave mirror after reflection it passes parallel to the principal axis. Reverse phenomena. Previously what happened? A ray passes parallel to the principal axis, after reflection passes through focus. If you place one mirror perpendicularly, the ray traces the same path. That means ray passes through focus. After reflection passes parallel. That is only rule number 2. Any ray passes through focus, either below the principal axis or above the principal axis. If the ray comes this way, goes this way. So here ray is coming this way, that is why it goes this way. Okay. Here also you see, if I draw the normal always passes through center of the curvature. Here angle of incidence is equal to angle of reflection. Light obey the laws of reflection. Okay. That is why anytime whenever the ray passes through focus, compulsory after reflection passes parallel, because angle of I is equal to angle of R. These two becomes equal only in that particular case. Okay. Right. And third rule I am going to tell you, rule number 3. See now this is the object is placed here. This is focus, this is center of the curvature, let's say. So now previously we have taken ray passes parallel, ray passes through focus. Now ray passes through center of the curvature I am taking. Ray passes through center of the curvature. Now you see, a ray passes through center of the curvature. Any ray passes through center of the curvature. What happened? After reflection traces the same path. Why? Because if you draw the tangent here, if you draw the tangent, so the line which is coming from the center of the curvature is perpendicular to the tangent. That is why the ray retraces the same path. Okay. So rule number 3 is I will write the rule number 3. Okay. First you note down the rule number 1 and rule number 2. And now rule number 3 we are going to discuss. See, a ray passes through center of the curvature. A ray passes through center of the curvature. After reflection traces the same path. Why, sir? Why after reflection traces the same path? Because if you draw the tangent here, tangent is the perpendicular line which we draw to the tangent is a line that touches the point at only one point, touches the circle at one point. This is tangent. So here the angle is 90 degrees. That is why after reflection the ray traces the same path. Okay. So this is rule number 3. A ray passes through center of the curvature. A ray passes through center of the curvature. After reflection traces the same path. This is rule number 3. Okay. So these are the rules to draw the ray diagrams. Rule number 1, rule number 2, rule number 3 we have discussed. By using these 3 rules, in the next topic we are going to draw the ray diagrams. Please note down this rule 3.